Kinematics, Variable Acceleration, Part 3. So we look at using integration to solve a problem this time. So we're given the velocity function, and we're told that initially an object has a displacement of 5 meters. So that's relative to this point, where the displacement is 0. The object here initially has a displacement of 5 meters. And we're looking for the displacement function. So this is given, the velocity function here, and we want to work out the displacement function. So we're moving in this direction, which means we need to do some integration, and we will get a constant of integration, but we're given the initial condition here, t equals 0, the displacement x is equal to 5, and we can use this to work out the constant of integration. So we integrate the velocity function, which is 6t minus t squared. We get a constant of integration. We have some initial conditions. So when t is 0, this term is 0, this term is 0, so c is equal to x, which is 5. So c equals 5, and so we have our displacement function in terms of t, time. So we can use that to work out the displacement when t equals 6, and all we're doing is substituting t equals 6 into here, and that will give a displacement of 41 meters. Example 5, we're given a velocity function. So we are here, and we want to work out distance traveled. In our diagram, we want to come in this direction, so some integration is required. So in the third second means this. So the first second is where you start a stopwatch and you go from t equals 0 to t equals 1. That's the first second. Second second, third second. In t equals 2 to t equals 3, the distance traveled in that time period. Okay, so we're going to do some integration, and again, it doesn't make any difference whether we're using the letter x for distance or displacement, or s or r. We just need to integrate our velocity function, which is right here, that's given. And this time we know the actual values of t that we're going to use, t equals 2 and t equals 3. So we integrate with those conditions attached. And that's pretty straightforward. Integrate, substitute in 3, substitute in 2. So the displacement is minus 14 meters, which means the distance traveled, which is always a positive value, is 14 meters. Make sure you don't confuse these two. Displacement can be positive or negative, but distance is always positive. Here is the velocity time graph. The equation of this graph was given here. V is equal to 5 minus 3t squared. And we can see velocity is positive to begin with, and then the object changes direction and velocity becomes negative. And between t equals 2 and t equals 3, the area here gives the displacement, which is why the integration gave us a negative value, because the area under the horizontal axis for integration always turns out to be negative. So we know the displacement is minus 14 meters, but distance traveled can't be negative, so it's 14. In our example, we've got something like this, where the curve is below the horizontal axis, so this is the area that we calculated. So our displacement was negative because the area is below the horizontal axis, but then we change the sign to get the distance. Or in this third example, where the curve is above the horizontal axis, then distance and displacement are exactly the same, and the area is positive. But in this one, we've got a mixture. So if you work out the area here, that will be positive anyway, and you work out the area for this region, which is negative, but you change the sign, For distance, you add them together. For displacement, it's what's above the horizontal axis minus what's below. For further practice, try these questions.